Okay, so we were talking about axiomatic. So we are now in the syntax part, and we want to say a formal proof system for first order logic, and it will have the same style as we had before. We will have axioms, and we will have deduction rule, and the deduction rule will be again modus ponens. So the difference is in the set of axioms, and the set of axioms will even be defined as an inductive set. So the set of axioms is the closure. So here are axiom types. And we said that the first one was substitution in a propositional tautology. And the point here was that we have to distinguish between propositional tautology and first order logical truth. Propositional tautology is something which is that its truth is the consequence of just the structure in terms of propositional connectives. So we take our formula, we parse it out with the propositional connectives, and we check whether what we get is a propositional tautology. What remains is important to note that there is an easy way to check it. If I want to check if a formula is a substitution in propositional tautology, it's easy to check. I just write a parse tree. I stop when the next when the next operation is not a propositional connective, and I check with the truth table if I have a tautology. I could have tried to go further and say, if I allow myself checking for truth, I could say, oh, every logical truth is an axiom. But then it turns out, and we'll see it later, that we don't have any algorithm that can check if a given formula is a logical truth or not. While we do have an algorithm that can check if a given proposition is a tautology, just a truth table, we don't have an algorithm, and we will prove that no such algorithm exists, that could check logical truths in first order logic. So it's very important that here the truth of this of such a statement is implied already by the propositional connectives. The next axiom should be, you see, this only talks about the meaning of the propositional connectives. It doesn't do anything about the meaning, the intended meaning of the quantifiers for all there is. So we need to give an axiom that will somehow say what do we mean when we say for all. So the axiom will be for all x alpha of x arrows alpha tx, and I'll have to explain this notation. This means that if I have a formula for all x alpha x, then I can take any term t and substitute for x. So alpha tx is just a notation. Alpha tx denote the formula obtained from alpha by substituting the term t for every free occurrence of x in alpha. So if I have, for example, the formula, say, so here is an example. Say I look at the formula that says, for all x, p of x, arrows p of x. Right? So that will be, let this be my alpha. And let t be some term, say I have a function symbol f of xy. So what will be alpha t substituted for x? What will we get? Anybody wants to try? Yes.
For every x, px, p, f, x, y.
Right. For every x, p of x, arrows p of f, x, y. So notice that nothing changed here because this x was not free. It was bound by the quantifier here. We only substitute for the free occurrences of x, and I substitute the term t for the free occurrence of x. So this axiom kind of tells us, it states what is the meaning of for all. If for all x, alpha of x holds, then no matter what I substitute for x, alpha of this t will hold. T, a term, just denotes an element of my universe. So if I have for all x, alpha of x, then alpha should hold for every term t. But we have to be careful about, so now we need to be a little bit careful about this axiom. So let me show you an example where this axiom leads to a formula that is not logically a logical truth. So we need a warning here. Consider alpha to be the formula for every x there exists a y such that not x equals y. So assume I have this formula. What does this formula tell me about the structure? What do I know about the structure in which this formula holds? It characterizes a set of structure. Which structures does it define? Yes?
Everything with more than one variable.
Right. It just characterizes all the structures with more than one element in the universe. Okay, now what will happen? So I have here something which is the form for all x alpha. So what will happen when I substitute y for x in alpha? What will I get? What will I get? Yes?
There exists a y such that y does not equal y?
Right. There exists a y such that not y equals y. And clearly, this formula doesn't logically imply this formula. Yes?
It's because the one y is not free, but we're kind of just confusing it by using similar notation.
Right. So the problem is, the reason that we got into trouble here, you see, here I said something that holds for every x. So I took some term to substitute for x, y, and suddenly I got into a very silly statement. And definitely, this is not a logical implication. Right? This will never hold in, no matter what structure I take. And the problem was, as you indicated, the problem is that the y here, the x here is free. But once I substitute it, it got captured by the exist y. So its meaning changed. From being a free variable, its meaning changed to being a variable that is bound by this there exist. So there exist here kind of put its hand over my free variable and made it a bound variable. So when we write this as an axiom, we have to make sure that So we have here a caveat, provided no variable in the term T becomes a bound in when substituting T for X in alpha. What went wrong here is I had, in my T, I had a variable Y that once I substituted, it became bound. Because there was this exist Y. If I used here another variable, if everything would have been fine. If I used the alpha of zx, that would have been there exists a Y such that it's not the case that z equals Y. And that will be fine. This means in my structure I have more than one element, and if I have more than one element in my structure, then that will be okay. That's satisfiable. Okay, so this is the next axiom, the axiom that allows us. Note that each of those axioms is actually an infinite set of formulas. Every formula of this form is going to be an axiom of type 2. Okay, so far we have two axioms. That's not enough because you see, the first axiom, in some way, the first axiom determines the meaning or validates the meaning of all the propositional connectives. Propositional connectives should work such that a tautology is an axiom. This axiom tells me what is the intended meaning of for all. For all x something means no matter what you substitute, it will be true. So what is missing? We have the propositional, if we look at the syntax of first order logic, we had the propositional connectives and we had for all. So what am I missing when I'm trying to set axioms that will kind of, I want them to be sound and complete, I want them to somehow capture the full meaning of my semantics. So what is still missing? If I do have something that tells me how to interpret connectives, and I do have something that tells me how to interpret for all, what may still be missing? What? There exists is just short. It's a good point, but there exists, we just view it as short hand for not, for all not. So there exists an X such that it is just short for, it's not the case that for all X it fails. So this is a good comment, but we can overcome it by just saying we want our syntax to be as simple as possible. We don't actually need the there exist. Whenever we see as there exist, we interpret it as a shorthand for this. So what is still missing? So that was a good point, but something else is still missing, even if we don't have there exist in our syntax. Think of axioms. Yes?
Equality?
What? Oh, equality is still missing. It's another good point, and I'm going to skip equality for simplicity. Right. But think of axioms like in algebra. I mean, I don't know how many of you have seen the axioms of a field or the axioms of a vector space. Right? So if I have a field, I have a plus operation, and I have a times operation, and I have axioms that tell me that plus is commutative and associative. And I have axioms that tell me that times is commutative and associative. And I have a 0 element, and I have a 1 element. Still, I have another axiom of the field on top of the one that tells me how plus behaves and how times behave. What else is there? We have, what? We have axioms that tell us how they interact. How times and plus interact. What rule is it that tells us how they interact in algebra? Distributive, right? It tells you that x times y plus z equals x times y plus x times z. So it tells me it's not enough to have axioms about plus and axioms about times. I also need an axiom that tells me how they interact. And it's the same here. I have an axiom that tells me what is the connective, the propositional connectives, what do. I have an axiom that tells me what for all is, but I need an axiom that tells me how they interact. So our third axiom is going to be every formula of the form for all x alpha arrows beta implies for all x alpha arrows for all x beta. So now we are almost done. Except that we need one more thing. We need something that tells us that if I add for all x to alpha that does not have x in it, what does it mean? And we want to say it is meaningless. It doesn't do anything. I mean, syntactically, I can write a formula like saying for all x, p of y. What does this formula mean? It just means p of y. So in order to capture it in our axioma, a proof system, we have another set of formulas which are axioms, and it is every formula of the form alpha arrows for all x alpha when x is not free in alpha. So these are our four groups of axioms. But these four groups of axioms are only a basis of a set of axioms that we define by induction. So the axioms are going to be, the set of axioms are going to be I of those four axioms, A1, A2, A3, A4. This is the four axioms are my basis. And I have an operation which is for all x, for all y, for every variable. Those are my operations. Which means if I have an axiom, I can add for all x or for all y in front of the axiom, and it will still be an axiom. So this is a very simple operation. It just tells me every axiom, it holds universally. I can add for all x, for all y. It was an axiom, it will still hold. Right, so for example, the formula for all x, and then I'll have here for all y, alpha arrows beta, arrows for all y alpha, arrows for all y beta. This is going to be an axiom because this was an axiom of type A3, and I can add universal quantifiers over axioms, and this will still be an axiom. And it will still be an axiom if I add here now for all z, whatever for all z I want. And this holds even if I have z or x free in alpha and beta. Okay, so these are my axioms. Now to get a proof system, we need a deduction rule. So the deduction rule is the same modus ponens that we had in propositional logic. It's exactly the same rule. And this gives me my proof system. So the formal theorems is I of the axioms and modus ponens, just like we had in propositional logic. So a formal theorem is anything that we can generate by starting with axioms and using modus ponens. So let me give you the first example of a formal proof. Here the formal proofs, although their set of axioms is more complicated than in propositional logic, they are much more natural. So here formal proofs are more intuitive. They're easier to derive. So here is a first example of a formal proof. And then again, I will denote it, the provable, by the same symbol as we were doing in propositional logic. I claim that it's provable that P of x arrows, there exists an x such that P of x. So this is a formula which I claim is provable from our axioms. So how shall I prove it? So here is a formal proof. So a formal proof should consist of a sequence where every line is either an axiom or the result of applying modus ponens to previous lines. So here I will start with, so first of all, just translate it to our formal language. The there exists is only shorthand for and for this. So actually what I want to prove is formally, this is the same as the formula P of x arrows not for all x not P of x. That's what I want to formally prove. Because this is the actual meaning of there exist. So this is what I want to formally prove. So I start with for all x not P of x, arrows not P of x. So why is this a legal first step in a proof? Yes?
Because not P of x implies not P of x is an axiom.
But how do I add the for all x there? Oh, if I use the last rule, then there will be a parenthesis here, but I don't have parentheses.
Oh, okay.
It's not for all x, this implies this, then you will be right. It's for all x, this guy implies this guy. So I cannot just say it's a generalization of something that was already there. Anybody sees which group of axioms it belongs to? Yes. What is 2? Yeah, 2. Because now, just note, this is axiom of type 2, and the reason is that note that if I take alpha and I substitute x for x, what will I get? I can substitute every term for x. If I substitute x for x, what do I get? Alpha again. Nothing changes, right? And this is always a legal substitution. If I substitute x for x, if I put x wherever x was free, it will not suddenly get not free because it didn't change anything. So this is always a legal substitution. So what I did is I used axiom type 2. I started with, for all x, this is my alpha. And this is my alpha with x substituted for x. Okay? Now what I'm going to write is that for all x not p of x, arrows not p of x, arrows p of x, arrows not for all x, not p of x. So why am I allowed to write this formula now as my next line in the proof? Yes?
I believe it's a propositional.
It's a propositional tautology, right. Because if I break it down to propositions, what I have here is, say, call this guy, say, A, and this guy, not B. So P of x is B, this is A. What I have here is B, arrows, not A. So if I just break it down with the propositional connectives as much as I can, I get the formula A, arrows, not B, arrows, B, arrows, not A, which is a propositional tautology. It's not a propositional axiom, but it is a propositional tautology. Right, it's easy to see. I mean, if we wanted this to get false, we will have to have true here and false here. We will have to have true here and false here. So we'll have to have A true and B true. And if A is true and B is true, then we get false here. So we could not have had the false overall. I mean, it's easy to check. This is a propositional tautology. So this is now axiom of group 1. Is a substitution in a propositional tautology. Now, what will be my next step? Modus ponens. Because now I have here the head of an implication equals what we already have before. So I can use modus ponens, apply modus ponens on lines 1 and 2, and I get P of x, arrows not for all x, not P of x, and this is exactly the formula that I wanted to prove. So I hope that you already get the feeling that those proofs are more intuitive. I mean, the proofs in propositional logic, the formal proofs in propositional logic, were just completely arbitrary. There's no way one could come up with them. Here it is kind of makes more sense. We just follow the reasoning of why is it true and try to formalize it. Okay. So we have our first example of a formal proofs. Any questions about this formal proof here? Yes?
Would it make sense to use the propositional tautology as first step?
For what? For this one.
Yeah.
So what you want to justify it as a propositional tautology.
Yeah.
But if I break it down as a propositional tautology, all I get here is A arrows not B. I can't get rid of the for all. As a propositional tautology, if I write this guy, if I write this guy, yeah, this is just some A. Here is arrows, okay, here is not, but here is something that is not using propositional connective, so it has to be a B. And A arrows, it has to be a B because it's not syntactically exactly the same as what I had as A. So A arrows not B is not a tautology. So the idea is we are allowed to substitute for sub-formulas, but we are only allowed to follow the structure that is dictated by the propositional connectives. We cannot do anything with the for all. This is a different formula than this, and there's nothing I can do about it. Okay? So now that we have a proof system, there are two steps that we want to take. First of all, we want to talk about proofs from assumptions. And that's a very natural definition, exactly the same definition as propositional logic. And then we want to show soundness. We want to show that if we prove something, then it's guaranteed to be always true. So let's do these two things. I will first define the notion of proving from assumptions because I want to start with the soundness in this general form. Okay, so we have a definition of proofs, formal proofs. From assumptions. So we say that we have a definition for a set of formulas gamma and a formula alpha. We say that gamma formally proves alpha if and only if alpha belongs to I, and here I will have axioms union gamma with modus ponens. So this is exactly the same definition that we had in propositional logic. The only difference is that now when we say formula, we mean first order logic formula, and when we say axioms, we mean these axioms. But there's nothing really new here. So we have the notion of proofs from assumptions. By the way, where the new assignment, was it uploaded already? Okay. And when is the current assignment due, the number 3?
Next Tuesday.
Next Tuesday. Okay, so we have this notion of proof from assumptions, and now I don't see any point of discussing it any further at this point because it's exactly the same notion that we saw in propositional logic. So let's move the next step and look at the soundness theorem. So what will be the soundness theorem? It will say that for every set of formulas gamma and every alpha, if gamma can formally prove alpha, then gamma logically implies alpha. You remember the soundness is a connection between syntax and semantics. It tells us that if we prove something, then it's a logical implication. Right? And in particular, if we put gamma to be the empty set, in particular, every provable alpha is a logical truth. We get this by setting gamma to be the empty set. If alpha is provable from an empty set of assumptions, and being logically implied by the empty set means it is always true. So how am I going to prove it? By induction, right? Because, you see, for every alpha, what does this mean? This just means we see it here. It's for every alpha in the inductive set. So if I want to prove something for every alpha in the inductive set, I will use induction on this set. So the proof is by generalized induction. And we can even say more on the structure, I of axioms union gamma and modus ponens. Right, this is, if I say if something holds for every alpha such that gamma proves alpha, I say it's the same as saying for every alpha in this structure, so I'm going to use induction on this structure. Now I have a problem with free space on the board because I want to keep the axioms, because we'll have to check each of the axioms. I want to keep the definition, I want to keep the theorem, and I also want to write the proof.
You can use the overhead projector.
Right. Or I can write on the screen or something. So let me erase this part and just summarize it. Just remind us what the axioms are. Without the comments, we can squeeze it. So what are the axioms? The axioms are, one, substitute in propositional tautologies, and two, for all x alpha arrows alpha tx when allowed. Three was for all x alpha arrows beta arrows for all x alpha arrows for all x beta. 4 was alpha arrows for all x alpha when x not free in alpha. And then we took all of this and say close under prefixing for alls. These are the axioms. Close this set under allowing a prefix for all. These are my axioms. So that's what we need to bear in mind. And these are the axioms with an X. Okay, so now we can get to the proof. So we want to do an induction on this structure. So what do we have to start with? Yes?
The axioms, the elements of
Right. The axioms are the elements of gamma. Okay, so induction basis. Case 1, alpha is an axiom. So I claim that we have here a subclaim. Every axiom is a logical truth. And even this we need to prove by induction, because the set of axioms is defined as an inductive set. So we prove it by induction on the set of axioms. So we have here induction inside an induction. But this one is very easy. So this is proof by induction on I of A1, A2, A3, A4, and adding the for all. This is the structure that generates all the axioms. So we have to show that each of those is always true. Right? So substitution in tautology, if you substitute in a tautology, no matter what the values are going to be, it's a tautology, it will be true. So nothing to worry about this. This has to do with our semantic definition of for all. We remember we said that for all, X, alpha, holds in a structure if no matter what we substitute for X, alpha of this element will hold in the structure. So that was a matter of our definition of semantics. So the definition of semantics guaranteed that this was the case. And here it's easy to check. We check it by way of contradiction. If this one fails, so let me just write it down. What happens if this fails? For all X, alpha arrows beta, arrows for all X, alpha arrows for all X beta, let us assume that this fails. So in order for this to fail, we need to get true here, and we need to get false here. So in order to get false here, I need to get true here and false here. And when does for all X beta fail in the structure? It fails in the structure if there is an element A in the structure such that beta of A is not true. So for this A, beta of A is false. What happens for alpha of this A? So there is an element such that beta of A is false in the structure. If in a structure this gets false, then in that structure there is an element A such that beta of A is false. What happens to alpha of A in this structure? Has to be true, because we have for all X alpha is true. So I have alpha of A is true and beta of A is true. So what happens in this structure to alpha of A, arrows, beta of A? What happens to this in my structure? If I have a structure, I already gave you the answer. If I have a structure in which this is true and this is false, then in that structure there is some A such that this implication is false. There is some A for which beta is false, and for all A alpha is true. So for that A, I get true arrows false. But if there is some A for which this implication is false, it couldn't be the case that for every X, alpha arrows beta holds in my structure. So this cannot be true. So I cannot be in the situation where this formula is not satisfied. So there are two levels of questions you might have in your head. One is if anything in my proof is not clear. The other question is that you ask yourself, so how do I write such a thing in the exam? So who has a problem with type A? That it's not clear what I did it here. Who has a problem with type B? How do we write it in the exam? Yeah, I guess. I guess so. So let me be a little bit more formal to show you how should you write it in the exam. So to write it formally, I mean, we're getting closer to the exam, so we need to be aware of how to write things. So how do I show, if I ask you to show that something is a logical truth? So if I want to write a formal proof to this, so we say, assume by way of contradiction, this is not a logical truth. Then there is some structure M and assignment S for which M under S does not satisfy my formula. For all x, alpha errors beta, errors for all x alpha, errors for all x beta. If it's not a logical truth, there is a structure, there is an assignment that make it false. Okay? Now, by the truth table of error, it must be the case that this M under S satisfies for all x alpha errors beta, and this M under the same S does not satisfy for all x alpha errors for all x beta. If an implication fails, it must be the case that the head holds and the tail fails. Similarly, we get for this structure M under S satisfies for all x alpha, and M under S does not satisfy for all x beta. Now we go into the definition of the semantics. By the definition of semantics, if M under S does not satisfy for all x beta, there exists some A in the universe of M such that M under S, when I substitute this A for X, does not satisfy beta. That was our definition of semantics. That was, I think that the notation that Aaron used was S hat, or in that semantics, S hat, when I substitute A for X, of beta was false. That's, I think, the notation that he was using. But I'm using the same notation as the book, as the Anderson book. What I don't like about this notation is that we don't see the structure here. I want to have explicit reference to the structure M. Okay? So now we can ask what happens with M in the same assignment A for X, what happens to alpha? And I claim that it is satisfied, since M under S satisfies for all X alpha. So the semantics of when will a structure satisfy for all X alpha, it will be if no matter what you substitute for X, alpha will be satisfied. So therefore, by the truth table of arrow, M under the assignment S where A substitute X, if I look at alpha arrows beta, this gets true, this gets false. So do I have here satisfaction or not? No. Because this got true, this got false, and I check the truth table. Now I go back to the semantics of for all. By the semantics of for all X, we get, this means that M under S does not satisfy for all X alpha arrows beta. And we got a contradiction. Because here we just said that in order for this to fail, we need M to satisfy for all X alpha arrow beta. And then we saw that if we want it to fail, we need M to not satisfy alpha arrow beta. So we got a contradiction. So our assumption that this was not, you see, we assumed, aware of contradiction, that this was not a logical truth, led to a contradiction. So if you write it so nicely in the exam, you'll get all the possible points. Is it clear? Okay. The other thing that's clear from this nice proof is that we do not have the time to go now for another one like this. So I'll just leave it to you to show that the other axiom, because remember, we are only in case one of our base case of the inductive proof of the soundness theorem. There is a base case and then the induction step.
Yeah. Of the base case.
Yeah.
There's an induction step of the base case too.
When the base case of the first case is the base case.
Exactly. Right. It's the base case of the base case. It's
The first case of the base case of the base case.
something like that. It is some permutation of case, base, and first.
The first case is the base case.
Okay.
Base case. Inductive case, which is the base case.
Okay.
Wait, we're
Base
proving for formulas. We're proving for the base case of formulas.
And
Then
the,
we're proving for the base case of axioms.
no, we're playing for the first case and the base case of formulas.
No, but axioms are also a inductive thing. So
Right.
the base case of axioms and then the first case of the base case of axioms.
It'll be funny to hear this on the recording.
No, wait, no. We just have the third case of the base case.
Okay, it's the third case. It's the third case of the base case of the first case of the base case. Okay. So we did this. Now we need to check this, which I leave you as an assignment, as an exercise for yourself, just because of lack of time. Now to finish the axioms, we need to see the closure. So to finish case 1, where alpha is an axiom, we have to see the closure under for alls. Right? So the induction step. This is the induction step of case 1 of the base case. And this is assume alpha is a logical truth. Prove that for all x alpha is a logical truth. Because we close under for alls. This is just to finish the case of axioms. And again, it's the same thing. So assume by way of contradiction that for some M(S), we have M under S does not satisfy for all x alpha. Because if it's not a logical truth, then it fails sometimes. Now, by the semantics of for all, there is some A in the universe of M such that M, when we substitute A for X of alpha, fails. Now, where do I get a contradiction? Yes?
That's saying it's not logical truth.
Right. This is contradiction, contradicting the assumption, the inductive hypothesis that alpha is a logical truth. Because we assume by induction hypothesis that alpha is a logical truth, we have to show it for all x alpha. And suddenly we got an assignment under which alpha fails. So this finishes case 1 of the base case. Right, let me just put here on the side what we are trying to prove so you will see what do I mean by case 1 of the base case. We need to show that if alpha is in I of axioms union some set gamma and the operation is modus ponens, then gamma logically implies alpha. And we now handle the case that alpha was an axiom. The base case contains, what else does it contain? Alpha comes from gamma, because this is the basis. So case 2, alpha came from gamma. So we are still in the base. If alpha didn't come from here, it came from gamma. But if alpha comes from gamma, this is just by definition of logical implication. So, but in this case, gamma logically implies alpha by the definition of logical implication. Because logical implication means whenever every formula in gamma is true, then alpha is true. Since alpha is one of the formulas in gamma, it follows from the definition. So we are done with this case. So we are done with the basis of the induction. Now the induction step. So what do I assume and what do I have to prove? See, so the right frame of mind is to view logic as a game. We have some rules of the game, you have to play by the rules and achieve some goals. It's just like Sudoku or something like that. So what is the induction step? Yes?
You assume beta and alpha implies beta?
What do I assume about them?
That they're logical truths? Or that
That they logically implied by gamma.
yeah.
Right. So we assume that why something is bothering me? Something here went, okay, so this is very easy. Okay, it's just too easy, but why worry about things being too easy? Assume gamma logically implies alpha and gamma logically implies alpha arrows beta, and we need to show gamma logically implies beta. Because the induction step, my operation is modus ponens. So the inputs to my operation were alpha and alpha arrows beta. The output is beta. And this is exactly like the case of propositional logic. If not, then there is some instance in which this is false. But this is always true. And if beta is false, I'll get contradiction here. So this just follows from the truth table of arrows. So this follows from the truth table of arrow, just like in the same proof for propositional logic. So we have soundness. We have the soundness theorem. Okay. So we have soundness. Now I want some theorems about proving from assumptions, and I don't think I'm going to have time to prove them, but let me just mention them. They're all natural and simple to prove. So some basic theorems on formal proofs. So the first one is the deduction theorem. Which says for every gamma and formulas alpha and beta, gamma union alpha can prove beta if and only if gamma can prove alpha arrows beta. And the proof is just like propositional logic because it's actually a statement about the arrow sign and modus ponens. It's about the relationship between arrow and modus ponens. So it's the same proof as in propositional logic, actually it's a simpler proof because now in propositional logic we needed axioms and we need to prove everything from axioms. Now we can allow ourselves any substitution in tautology. So we have, life is much easier. We just say this is a tautology. So I leave this to you. And I will state, how am I doing time-wise? 2 minutes. I will state one more theorem that is completely analogous to propositional logic, and the theorem that is special to first-order logic we will do on Thursday. And then we will have what? How many weeks we'll have left? 1 week. There's so much I want to do. Okay. Okay, so the next one is just says that, so theorem 2, the following are equivalent. So one of them is saying that there exists some beta such that gamma cannot prove beta. And the second one is for no alpha does gamma prove alpha and gamma proves not alpha. And if this holds, in this case, we say that gamma is consistent. So the definition of being consistent is exactly the same definition as propositional logic, and it's one of these two equivalent definitions.